Okay, so this is a recording of the notes for 4-2. At the beginning of the hour, I gave back, two things, and actually I'm saying this to everybody. I gave back the self-quiz from the other day, and that is for you to look at. If you want to see how to do the problems, they're on the Yola site under the lesson for whatever number that was, 4-1. And the second thing I gave you was the pre-test, post-test for chapter 3. Will you look at that and then put that back in the group folder? So if you were gone today, it's in your group folder. Look at it tomorrow and then put it back in the group folder, and I'll try to remember to say that as well. Our goal is to get done with the notes for 4-2 today, and you are going to take the quiz tomorrow. On this section, this is applications with angle measure, and we know that theta equals S divided by R, and that S isn't my favorite kind, but there's three related equations here. So theta equals S divided by R equals S divided by theta, and S equals R times theta. Do you agree with those three related equations? And so, if I multiply both sides by R, I'll get R theta equals S. If I then divide by theta, I'll get that R equals S divided by theta. So these are always, if two things multiply to be a third, you can always get these three little relationships as you go. One thing I'll caution you about, as soon as we start talking about arc length in a trigonometric setting, as opposed to a geometry setting where we were not looking at trigonometry, we need to make sure that we are measuring our angle in radians, okay? So if you're given an angle in degrees, you just have to change it to radians. But please make a note to yourself of that. And so this is arc length. And, earlier in this section, we said what the angle was, I think theta. So if theta is the central angle of a circle and R is the radius, then the length of the intercepted arc, S is the length of the intercepted arc, which is the piece of the circle, and S is equal to R theta. R has to be in radians, and I wrote central angle, I'm going to add in radians. R has to be in radians. So the most common problem with a problem like this is I use degrees accidentally, and then it's not going to be the same thing. You can use degrees and work it out and figure it out, but it's not using this formula. So when theta is measured in degrees, you can also use S equals that, but we don't even go over that, which kind of just, as you're doing it, converts it. But we just use that S equals R theta as we go through this. And so arc length. The first one here, 4A, is find the length of the intercepted arc in the circle with a central angle measures pi over 3 and a radius of 4 inches and round to the nearest tenth. So they're pretty much in this one just telling you everything you need to know. And so S equals R theta, we'll just write that down. In this case, R is 4 inches. Theta is pi over 3. And you'll notice this. Remember that, and this will maybe jog your memory as to why you can't use degrees. This is unitless. This angle theta, pi over 3, is a unitless ratio. And so when we multiply these, we're going to get inches, which is exactly what we want, a length. You know what I mean? And if we had degrees, we would get something called degree inches. And that's not the same as inches. So we want to be super careful as we go. So S is 4 times pi over 3. They told us to round it to the nearest tenth. And Nolan, go ahead and tell me what that is to the nearest tenth. 4.2 and inches is our label for that one. So just a very straightforward problem to start out with. The next one is going to be the same exact kind of problem, but we're going to trip ourselves up by saying, oh, it's going to be degrees, and then we'll kind of see what happens when we have to do that conversion. So 4b, we're told that the central angle, theta, is 125 degrees. We're told that the radius is 7 centimeters in this one. We know that S equals R theta. But before we do theta in this one, we have to convert theta into radians. And so the little easy rule of thumb, generally, degrees does not have pi in it, and generally radians do have pi in it, so that can help you with that conversion. So if I want to end up with pi in it, in order to convert that, I'm going to multiply by pi over 180. And in this case, you know, you're not asked for that angle, so if you want to reduce it, you can. If you don't want to reduce it, it's not a big deal either way, but it's going to be 7 times 125 pi over 180. If you did reduce it, 7 times, I think it's 25 over 30, pi over 36. So either answer or either way should give you the right answer. So S is approximately equal to, oops. To the nearest tenth, Peyton, what did you get? 15.3 centimeters. So I wanted to go through arc length pretty quickly because that is very straightforward. It's this next part that sometimes gets people, and that's linear speed and angular speed. And so I want to make sure that I have enough time to spend with linear speed and angular speed. And so here's what's happening. The formula for arc length, which we just looked at, can be used to analyze circular motion. And the rate at which an object moves along a circular path is called its linear speed. The rate at which an object rotates about a fixed point is called angular speed. Okay, so kind of maybe reread that to yourself just so that you're understanding kind of what it's talking about. The rate at which an object moves along a circular path is called the linear speed. And then the rate at which an object rotates about a fixed point is called the angular speed. So one has to do with kind of rotation, and one has to do with, well, it's a rate, but with that kind of distance. Linear speed is measured in units like miles per hour, whereas angular speed is revolutions per minute, okay? So, you know, if I'm on a Ferris wheel, I don't even know, and I'm going, you know, 100 meters per minute, I don't even know if that would be reasonable or not, then that's my linear speed. If I'm telling myself revolutions per minute and kind of, you know, an engine thing, how many revolutions is it making in a minute? Well, I just said in a minute, so it's maybe making 1 revolution per minute, or maybe it's making 5 revolutions per minute, or whatever the case may be. And they give some equations here. I'm going to give some other ones as well. So linear and angular speed. And we do expect a constant speed, or we treat it like a constant speed, even if it's not. And along a circular path of radius r, so we don't like speed up and slow down at the beginning or the end. So if s is the arc length, and I will go back to my cursive s just so that I don't have trouble with that, and the arc, if s is the arc length traveled by an object during a time t, then the object's linear speed v. So linear speed and v is called v, or equals v. I'll maybe put that there. And v is equal to s divided by t. So v is the linear speed, s is the arc length, so s is arc length, and t is time. Whatever dynamic of time that we have. Now, I'm going to give you an alternate version of v that's not written here. And so remember a minute or two ago, or a few minutes ago, we said s equals what times what? What does s equal? What times what? R times theta. S equals R times theta. So our alternate version of this is V equals R theta divided by T. Because sometimes people will say, but wait, they didn't tell me the arc length, or they didn't tell me this dynamic or that dynamic. And I want you to know that you can still figure that out. And I'm also going to, this is all about linear speed right here. I'm going to just remind you or say linear speed, and I'll change colors when I start talking about angular speed, is the rate that object moves along a circular path, along a circular path. And you might even put like miles per hour, something that's recognizable for you, feet per second, things like that. So that can help you also decide, because sometimes it's hard to decide whether you're talking about linear speed or angular speed. So that's all linear speed. Then if theta is an angle of rotation in radians, and by the way, our angles are always in radians when we're doing these things, through which the object moves during the time t, then the angular speed, and this is called omega. It's the lowercase Greek letter omega, because the uppercase one looks different, but this is the lowercase, and I kind of make it like a W that kind of curls into itself a little bit. So that symbol is omega. Omega. And so this is angular speed. Omega, and that's as close as I'm ever going to get, omega. And that is omega equals theta divided by t. So that angle that we're going through divided by the time for that. And so then just kind of some making sure we understand angular speed as well. And this is the rate an object rotates about a fixed point. And it's this omega equals theta divided by t. And if you look up here, can you see the angular speed in the linear speed? Look at that. Could you see that in there? So this theta divided by t, that's another reason we use this version also. So linear speed can be s divided by t, that arc length divided by time, or it can be r theta, because that's the same as s divided by t. Well, theta divided by t is that angular speed as well. So just some things to kind of remember or look at as we go. And I'm just going to tell you right now, sometimes we give our answers in terms of pi. And so then it's kind of an exact answer, so to speak. And sometimes we'll give our answers as a decimal as we go. So here's our first problem. And this is kind of come back because people I've seen at Christmas time record players and records and things like that. So a record player is just an easy thing, it just spins around, it doesn't really go anywhere. So it's an easy thing to kind of think about in terms of these questions. A typical vinyl record has a diameter of 30 centimeters. So first note to self is what? The diameter is 30, so the radius is 15, right? So kind of thinking about that. When it's played on a turntable, the record spins at 33 1/3 revolutions per minute. And find the angular speed in radians per minute of a record as it plays, and then round it to the nearest tenth as we go. So for this one, we're going to look at a couple of things. The first thing I'm going to do is I'm going to use, it's asking me for that angular speed. So I'm going to just say omega is theta divided by t. So I have to think about what my theta is here. And this is going around in 33 1/3 revolutions per minute. So if I want the angle that goes, 1 revolution is how many radians? No, just ignore that. If I just go around one time, that's 2 pi. Do we agree? That's 2 pi, 360 degrees, or 2 pi. So then now kind of think about what you said about 33 1/3. So really, to get our angle, it's 2 pi, 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 2 pi. How do I get that angle? 2 pi times 33 1/3. Does that make sense? So our angle, or theta, is 33 1/3 times 2 pi, and that'll still be in radians. And so I don't know, because I don't have a calculator, is that 100 thirds pi? And so I'm not going to reduce anything until I get to the end. And so I would say that, am I right? 99 and 1 is 100, right? So this is 100 thirds times 2 pi. And so this is 200 pi over 3. So that's my angle. And I'm not going to round anything to the end, just... it's a mixed number, 33 1/3. 3 times 33 is 99, plus 1 is 100. Yeah, so I don't know, that's how I would do it. Or you could, if you're using your calculator, you go a 33 plus 1/3, and 66 2/3 pi radians. Yes, if you multiplied this times that, yep. And so I just wanted to get rid of that adding dynamic in there for my own personal thinking of it. So if it did these 33 1/3 revolutions, then that's times 2 pi, that's my angle. And we've talked about this spinning angle idea. What is my time in this situation? What is my time? Revolution, it went 33 1/3 revolutions. How long did it take? 1 minute. So in this case, it's just 1 minute. It's not like, if it had said that was in an hour, then, we'd have to figure out how many minutes that was or whatever. And so we aren't really concerned or interested in that. So then for this one, when we put that in, omega is equal to 200 pi over 3, and that's radians. I'm going to actually write that just so that we know. Radians divided by our time, 1 minute. And so we might say that as radians per minute. And since we're dividing by 1, its omega is equal to 200 pi divided by 3 radians per minute. And then as a decimal, somebody could tell me what that was. 209.4, rounding to the nearest tenth, radians per minute for that one. And that's that omega. So that is the angular speed. And angular speed talks about, like, kind of revolutions per minute, in this case radians per minute, or whatever the case may be. Now we're going to do the same thing, or the same information, and this time though we're going to be asked for something different. So typical record, diameter is 30 centimeters. Oh yeah, I kind of commented on that. Did we even use the diameter or the radius in that last problem? No, because we were finding the angular speed. I'm guessing we're going to find the linear speed also, so that's why it's there. Same thing, 33 1/3 revolutions per minute. Now we want the linear speed, and notice this, it says the linear speed of the outer edge. Why does it say that? Right, so I'm going to know my radius is what? 15. And so, if it said I was like, I don't know if it would even say like halfway, between the edge and the center or whatever, it would be 7.5 or something. So we do want to kind of keep that in mind. I'll just remind myself the diameter is 30 centimeters, so the radius is 30 divided by 2, or 15 centimeters. Theta was that 33 1/3 times 2 pi, and I said that was 200 pi over 3. Is that right? That's how I said it, because I don't have a calculator or anything. And so there's r, there's theta, and so now we need the linear speed. And for that, we're going to, I'm sorry, I'm kind of feeling a little, okay, so V equals R, well, I'll write both versions of that because one is in the writing here. V equals S divided by T, or R theta divided by T. And what's the only one I haven't written down? Oh, T, what is time? Well, right this second, it's 1 minute, right? I mean, revolutions per minute. But yes, I'm glad it's 1 minute. But here's the dynamic that we have to be careful of. We want our answer to be in centimeters per second, right? Is what it says here. And so our time is 1 minute. So how many seconds is that? 60 seconds. 60 seconds. So we do have to kind of read carefully. Centimeters, we're good to go. And so now our linear speed is, 15 centimeters, which is our radius, times that 200 pi over 3, all over 60 seconds. And I wrote seconds here, so that was centimeters. I'm going to write it up here because do we remember that I had written this as radians before, just to kind of be able to say it that way, but this is unitless, right? So I don't have to include radians, and then I'll have it in centimeters per second. And so It doesn't say to round to the nearest tenth, but let's. So the linear speed is approximately what? Say it again. Something different. Oh, then maybe times by 15. So the answer before was this one, and you divided by that. Yeah, right. So 52.4. 52.4 centimeters per second. And so I'm hearing some different things. Maybe check, oh, okay, maybe check on there as you look at it. And I would say generally for students, this is the most challenging part of this section. It definitely is. So make sure that you're focusing on those problems and checking them over as you're doing your homework. And, you know, it might even be a section where you would try a couple odd problems because you'll have the access to the answers ahead of time as you go. So the next part, so this is in the middle of the lesson and it's the hard part. So do you remember what we did yesterday? Convert from degrees to radians. That should be pretty straightforward, just remembering the ratio. The rotation of the angle, adding 2 pi r, or 2 pi n, I think it is, or adding 360 n to get multiple rotations, a positive and a negative angle. So all of that's pretty straightforward. I would say this is the most challenging part of the section. And then really this is another easy part. The only hard part about it is remembering the theorem, or the formula here. So this is the sector of a circle, and you've had that before. And way back in geometry, we had a formula for the sector of a circle, and essentially, because in geometry we never do radians, the formula converts to radians, you know, but it's part of the formula. But now we're going to use our angle in radians. Theta is going to be measured in radians. So again, that's like the big thing to remember. So a sector is a chunk of the circle that is a region, and it's along the lines of area. So a sector is a region bounded by the central angle and its intercepted arc, so a piece of the pie, so to speak. And so we're going to find the area of the sector of a circle. A equals 1/2 r squared theta. And so there's a little bit of an explanation here, but I just want to make sure that I get through this. It's kind of that ratio idea and setting up a proportion. The area of the sector over the area of the circle is equal to the same ratio as the arc length to the circumference. And so when we put in the formulas that we know for those things, we can get this. R is the radius, and theta is the central angle in, theta is the central angle in radians. And more than anything, that's the thing to remember as we go, that it has to be in radians. So if it's not, we have to convert it. And that's something that we did in that last part. So here's our picture. Find the area of the sector of the circle, 6a. Our angle theta is 3 pi over 4. And so that is in radians. And then our radius is just listed here as 5 meters. So more than anything, we just have to make sure that we remember the formula. So area is 1/2 r squared theta. So area is 1/2 r squared, 5 squared. Make sure, because I've noticed things like this happening during this school year, never ever multiply that 1/2 times 5 and then square it, right? Because it's 5 squared, and order of operations says we do powers before we multiply or divide. And then times theta, 3 pi over 4. So maybe just take a moment and get that one on your calculator so that you can kind of see what that looks like. And this one did not say what to round to. Oh, and sometimes I will just say, we could get an exact answer here, correct? Anytime you're asked for an exact answer and it's something related to an angle and it's in radians, probably pi is in the answer, you know, so we could get an exact answer. Let's see. 25 times 3, 75 over 8 pi. Right. And then I don't know what it is, or I do, but what is it as a decimal to the nearest tenth? 25.9. What is my label? Yes, meters squared, square meters, because we just want to make sure that we're careful and its area so that we square that as we go. Then we have one more of these, and this is the same kind of problem, 6b, but here our central angle theta is 60 degrees, so that's an issue, right, that we'll have to just deal with, and our radius is 8 feet. By the way, just always make sure it is truly the radius that you know. You know, in these pictures, it's pretty easy to decide. Anybody know off the top of their head what 60 degrees is in radians? Yeah. Yep. So as time goes on, we're going to want to know those 0, 30, 45, 60, 90 angles in radians. And so 60 goes into 180. So pi over 3 is our angle. Area is 1/2 r squared, 8 squared, pi, theta, r squared theta. Pi over 3. There we go. And so see what you get for that one. And we'll just round to the nearest whole, or tenth again, to the nearest tenth. Any thoughts? 33.5 label. Feet squared for that one as we go. So that is all of the problems, and I did want to feel committed to getting through that. I will be here tomorrow. It may not seem like I'm here. We have a TrigStar competition for pre-calculus, so I will be out of the building, but I'll be back at the end of 5th hour. And so tomorrow we'll green pen and turn in homework 2. You'll isolate and take the quiz, and then we'll move on to the unit circle.